I am going to talk a little bit about object-oriented programming, and then basically what's left of object-oriented programming if you take away inheritance. Then I'll talk about some ideals that I think are important, and then I'll show how this is rooted in C++, what I'm going to say further on, and then I'm going to give some examples. Object-oriented programming is often defined as encapsulation, runtime polymorphism, and inheritance. And so basically what I'm talking about is what happens when you take away the last 2 bits. And if you look at what Christen said, he didn't talk in terms of language features very much. And so he talks about modeling your application domain in code. And I think that's a very good idea. And so what I'm talking about is how to model it in code, the bits that can be done well, and how it can be done well without inheritance. I remember talking to Christen about it, and I was saying, well, the defining aspects of object-oriented programming is encapsulation, runtime polymorphism, and inheritance. And he said, yeah, well, no. You can also do it without inheritance. And some of you have heard him say that, addition didn't become useless just because somebody invented multiplication. Therefore, the techniques to do with data abstraction and simple objects not in hierarchies did not become useless or irrelevant just because somebody like Christen invented inheritance. So I'm going to talk about that, and my take on object-oriented programming is basically to take the ideas of Christen's, of what's often known as the Scandinavian school of object-oriented programming, and apply them in the domain of systems programming without any excuses, meaning that I'm always considering myself under pressure for speed, compactness, access to hardware, and minimal runtime support. I know that this is not everybody's world, but somebody has to live in it. Otherwise, where would you get your compilers, your operating systems, your virtual machines from, for starters? So that's my world, and I'm going to talk about it. So context is C++. It's a statically typed language. It's for constrained environments, constrained applications. There's lots of support for it with different compilers, and there's an industrial ISO standard, and most of the use is in industry. And just to carry that talk a little bit more, I'll say that we succeeded. At the first ECOOP in Paris, I gave a talk, and I ended up expressing a wish that I would see the last object-oriented programming conference, because once it was universally accepted, you wouldn't need an object-oriented programming conference. And here I see that people actually are not talking that much about object-oriented programming. They are talking about other things. We're one. Okay? That's the point. Took a few years. And I'll show a few examples to show how deep into the world our code has gotten. Of course, I chose C++ examples because I will only use a few slides, and well, there's enough C++ to keep us going for the rest of the day. So there's some rockets there, there's the internet, there's the experiment down at CERN, Wall Street. There's some names of C++ applications there. People are always trying to drag me into language wars, but I have a principle that I don't want to say something bad about C++ applications, and for that reason it's really hard to say anything bad about a lot of languages. So to give you an idea of the size of this kind of thing, look at the ship's engine there. At cylinder head number 5 is an engineer. He's checking out the fuel injection system. which of course is a C++ program. So if this code doesn't work, you will see a ship drifting in the Pacific, and you'll see it on your, in your newspaper on your screen the next morning. Since you haven't seen such a ship, and since these things have been deployed for more than 5 years, it is possible to have really reliable code. And the hardware support there is limited.
Could you explain the Lego?
The Lego? What do you think they write this stuff in? Okay, anyway, there's some virtual reality there, there's some chip manufacture. The blood analysis thing is interesting. It's people who needs to put blood analysis in the ambulances so that when you come out and you find some guy who's fallen off a motorcycle, you have to figure out what is in his bloodstream before you give him medication, because the reason for him falling off his motorbike may involve things in his bloodstream. So there's another small specialized application. There's some more systems there. If you're into games, you'll know it. The red thing at the bottom is a distributed computing system on wheels. Anyway, so enough about that, but just to point out, from the point of view of 1986 and the start, or was it 7, at the start of ECOOP, we have actually won. We may, some of us are onto other things, but this is the world we live in. So my question here is, what's left when you take away inheritance? Well, there's still encapsulation. For those of us who likes data and state sometimes, that's important. And we have static polymorphism. There's other ways of getting polymorphism than using a virtual function table. And we have composition. So I'd like to emphasize this is not an anti-inheritance talk, anti-runtime polymorphism talk. We can still do that, but by definition, I'm not going to talk about it here. And we're exploring the alternatives. I mean, inheritance is still a major part in the set of tools I'm using and recommending. So if we have no inheritance, we get rid of an indirection. And that's important if you are short of memory and if you're short of cycles. And we don't need to recover information, type information, because we don't lose it. We don't need the equivalent of virtual functions or dynamic cast in C++ is kind of in some languages. And we get a simpler composition of abstractions because everything is represented by something that is fixed in size, fixed in function, and that simplifies things. There's no sort of variable sized object in this world. And so let's look at what we have. We have the plain old data, possibly encapsulated. We have simple classes with invariants usually, complex numbers, dates, messages, transactions, actions, things like that. Nice little classes, very useful. Quite often they don't fit into a hierarchy anyway. Containers, of course, all the containers we use, vectors, lists, maps, and such. The problem we have to deal with is interfaces. I mean, I think that's probably the most characteristic thing for object-oriented programming with inheritance. You can have a base class, abstract base class, interface, whatever you call it, through which you can access classes with different implementations, different sizes, but presumably equivalent behavior if you apply the same function. What we have more, so we need to deal with that. And we need to, and we have handles, which is in this kind of world what you have when you need variable size things or things that are spread over multiple places. You need to give them one of these nice fixed sized, fixed function handles that manipulates the rest. And so the key issues here for dealing in a world like that is abstraction and resource management. And I'm going to say a little bit, maybe 4 slides, on resource management. but I'm going to focus on abstraction here. If you want to know more about resource management, you need to get yourself a time machine and go back to Tuesday afternoon, and you can get that talk. Probably it'll be available on video somewhere. So basically, let me just go back to the early days of object-oriented programming. I started with Simula in 71, and my work with C++ is about a decade later. But basically, we've got classes with constructors and destructors, which is key in C++. Inheritance was actually there, the very early thing, but not virtual functions. I absolutely failed to convince my colleagues that it was useful. The basic attitude was that you must be nuts. If you want to call a function and you don't know which one it is, you haven't done your analysis right. In the end, I gave up and just implemented it anyway. Encapsulation was there, right in the front, public and private. Protected came in '86, and it's still a bit doubtful, especially for data. And the key thing was sort of overloading was there, starting with constructors and assignment and other things, and was general in '85. Overloading is in a way is a way you can get the ability of having similar behavior invoked with a single name without having inheritance. And then generic programming, the idea that you want to parameterize your vector with the vector element type, and you want to have a sort that works on every container and every element type, was there early on. I really messed up the implementation. I said, okay, macros will do that. Well, they'll do that if you are about one guy and not writing much code. And it doesn't scale, so it took me some time to get over that. I had in the early days also the notion that there was values and there was immutability, which has turned out to be useful also, even though the object-oriented world doesn't seem to have warmed to that idea very, very much. But I never could understand how you could program without knowing that at least some of your data didn't mutate or could control when it mutated. So a key thing in C++ is a resource. A resource is something that you acquire from somewhere and have to release later. Usually you acquire it explicitly, how else do you know you want it? And you would like it to be implicitly handed back, because if you have to be explicit about it, you forget and you get leaks. And the way we deal with this is the constructors, destructors, and a lot of objects look like that handle. There's a handle that controls access and ownership, and behind that interface is something else. Like it could be a vector and it holds a whole bunch of objects, or it could be a thread handle and it holds a set of pointers and data that interact with the operating system. That's a very useful thing, and constructors establish these things and destructors clean them up. And if you can assure that every object has an owner, you don't leak, and that's an important thing. So in C++, we have a whole bunch of resources. In the standard library, vectors, lists, maps, hash tables, sets, strings, thread handles, lock guards. iStream, OStreams are things that it could be file. Yeah, there's if in that one, that's a file handle, and so on. The point here is that, first of all, we can control their lifetime. And so they come into existence and they disappear at the earliest opportunity, and that takes care of release. And they're not just memory. The release action in a destructor may be closing a file, releasing a lock, going recursively down a set of containers and clearing up what's down there, which again may or may not be just memory, meaning that you can't get a garbage collector to to do it, unless you're so backwards you think finalizers are a good idea. And the whole control system here is through scoped objects, as I basically said. And this can be done with no overhead compared with doing it by hand. This is important. The systems programming and embedded systems programming and the C world are absolutely obsessed with performance. And I sort of have a rule of thumb which is called not a byte, not a cycle. That's what I mean with efficient compared to some gold standard in that field. I call it the zero overhead principle. So here's how it's done with a bit of code. I will show code, a fair bit of it. I feel an absolute fraud if I don't. So here is a vector. It's a vector of some element type T. You have a constructor there. That's the one that takes an initializer list. You have a destructor, which cleans up whichever mess is left behind. And there's a representation, which you can't see, but the compiler can see, so you can optimize well. No spurious indirections. If you want an indirection, you have to program it in. You can actually see one on the screen. The pointer over to the elements is the indirection, and the vector controls it. So you can declare a vector of doubles, give it an initializer list with some numbers. You can make a vector of string, and there's some famous language designers there. The point here being, then you use them, and at the end of the scope, the end curly, it's all cleaned up. And whatever resources was acquired by the objects in that scope will be released at that scope. There are people that say that their favorite C++ language feature is the end curly, the end of scope, because that's where all the magic happens. This means that resource retention tends to be fairly minimal. And there's just one thing left. What if you don't want things to go away at the end of the scope? And traditionally in older C++ code, you get a lot of pointers. People do things like they want to make a matrix, which is a sum of two other matrices. So they make a new matrix, they put it over on the dynamic memory and return a pointer, and now they have memory management problems. That's a dumb idea. But we've been doing it for a long time. That was the way it was done in Simula. That was the way it was done in early C++. C++ 11 systematized the best solution we had found to that problem, which is moving things instead of copying it. I mean, look, only a computer scientist would get something from here to there by a copy. You make a copy of this thing, you put the copy there, and you destroy the old one. That's not the way we do it. Even babies can do this. It's only one object, it moves. And the way this is done is that most of the interesting objects, essentially all of the interesting objects for which there is a problem, they are handles. So what you do is you take there's a representation in the handle, and you steal it. You can see there we have a nice object R, which we filled up with the answer. It's a local object, so it sits there. But you know, only the handle sits on the stack. The rest is over on the side. So we steal that, put it into res, which was on the outside, clear out the representation of the original so that when the destructor comes about, basically nothing happens. And now we have gotten, say, a matrix 10,000 by 10,000 out of a function at no cost. So we can move things around between scopes, and that's the remaining part of the puzzle. So if you want to, you can still deal with pointers, and you must deal with pointers if you do object-oriented programming with inheritance. So I mentioned this again. But we have smart pointers that keeps track of lifetimes. So basically a shared pointer is like an old-fashioned garbage collector, except that it gets resource release correct. The unique pointer is a similar thing, except that you only have one owner, and therefore you don't need a use count. But basically, if you use C++ as a modern language, it doesn't leak. And it doesn't run any slower than it used to. And actually, a lot of useful programs in the past use these techniques, but not systematic. these days you can be systematic about it. So basically, if I see a delete in a program, I assume there must be a leak somewhere, because if there's one delete, maybe you forgot another one. Furthermore, if there's a delete, there must be a new somewhere. So if I look at the new, and it's not inside a resource handler or resource manager, I assume there should be a delete somewhere, and if there's a delete, there's probably a leak. So don't put news and deletes out in the application code. They don't belong there. It just creates trouble for you. And if you've seen object-oriented programming, they have a lot of news in them, right? That's old style. We can do better. So enough about that. I'll go to the abstraction mechanisms. In 1980, I was recommending that you used a form of generic programming, parameterize your containers, parameterize your algorithms, and I recommended macros. That did not scale. It, as I said, worked with one man and his dog, but not with much more. In '87, I designed templates, and I had 3 aims. They should be extremely general and flexible. I mean, my formulation at the time was, if it can only do what I can imagine, I've failed, because my imagination is not up to the imagination of a group of smart people. Furthermore, we have to have zero overhead. We have direct competition with C, and sometimes with assembly code. So if I have to pay, say, for a simple access into a vector, an indirect function call, we're dead meat. There's lots of applications for which this is not true. There's lots of applications where you can afford 10 indirect function calls to access something. It's fine, lots of people do. But in my core domain, that's simply not true. And so a lot of stuff would have been in C with no abstraction, no guarantees, if I didn't have that principle. And finally, I wanted well-specified interfaces. Of course I want well-specified interfaces. I mean, I remember when C didn't have function argument types in interfaces. In other words, if you did square root of 2, you got a core dump, a segment fault, if you speak modern. And I didn't think that was a good idea. So I was the one that put function prototypes into C++ about 10 years before they came into C. And so I know the value of interfaces, but I did not know how to get all of those 3 things at the same time. And I don't think that at the time anybody else knew it. Like, everybody knew how to get this kind of abstraction stuff if you could afford a table of functions. No problem. Just specify a set of interfaces and you can get a nice generic interface. But I couldn't afford it. And so, well, 2 out of 3 ain't bad, but it isn't good either. So we managed with, without proper interfaces and generic code for, 10, almost 20 years. And it was a massive success. You have undoubtedly this morning used a program that depended on it. It's that widespread. I don't know which computer you use or which programs you're using, but maybe you used a telephone or something like that. It's a huge success even without that, but I felt so bad about it. So templates basically says, well, there is some kind of type that's the argument type. And that way you can say a vector of integers or a vector of strings or something, and you can do operations on them, sort the vector, and the sort can be written generically, so it could take a vector, it could take a list, it can take lists of strings, vectors of integers, all of this kind of good stuff. Basically, what was provided, which it was in modern terms, compile-time doc typing. Templates provides a Turing-complete, purely functional language with doc typing at compile time. People have done various things with that, up to and including implementing Lisp at compile time. So this has been very successful. It gives template metaprogramming, which I am sometimes a bit doubtful about because you can do really weird things. What was it people did last week? Tetris? Anyway, and it gives spectacularly bad error messages. The problem with doc typing is that when the doc quacks as expected, everything's fine. But when you get something wrong, when the semantics of the operation get wrong, or you 20 function calls down in a call chain find an object that does not have the quack operation, the error messages are spectacularly bad, like hundreds of pages of error messages showing all the guts of your library. It's not good. And the basic fundamental thing, and even worse, you get latent bugs. You ship a library and you haven't tested it properly, it gets used a year later in a context with some types you haven't heard of, and the problem happens. I don't like latent bugs. A lot of the C++ code is critical. Critical as in when it breaks, people die or get ruined. So we have to be serious about this. So let's look at a generic interface, something we have in the standard library and used for a long time. Just as an example, a sequence is a pair of iterators showing the beginning and the end of a sequence. And I don't have to say what the sequence is. The abstraction says that if you want to get the next element, you do ++. If you want to get the content of the element you're pointing to, you use a star. Doesn't care whether it's a vector, a list, or a map, or things like that. Good stuff. And notice there's no iterator base class, no indirect function calls, so we're still in the no inheritance domain. And this stuff can be as fast as you would handwrite in assembler or C. And that's what we've been using for a long time. The only point is that we haven't quite been able to say what it is we are doing from a type point of view. We can go further. That abstraction, you can parameterize the algorithms with the container type, with the element types, with predicates. I mean, is something equal to something else, something less than something else? Comparison criteria, actions, what do I do when I find something? And whole algorithms can be passed along that way. They're called function objects in old C++. Today we have the lambda notation for expressing it. And this gives fairly extreme flexibility without losing the performance. So I can write things like I have there on the screen, find f. So in f, find the first element that meets the criteria. The criteria is a lambda function that compares its argument to a griffin. We are obviously trying to find mythical creatures or something like that. And it returns an iterator to that element. The lambda notation generates either a function if it's a simple thing, or a function object if it needs to bind some context into the operation. That's C++ 11, but the techniques with function objects and algorithms like that goes back to 94 thereabouts. The picture here is by Alex Stefanov, who invented the STL and articulated a lot of these techniques. So let's look back at this doc typing. I mean, there's people who like doc typing. I'm not really one of them. I find it's painful for debugging. It leaves latent errors behind, and anyway, it forces people to think in a different way from what we do in the rest of C++. Because it really is a different way of thinking about things. And furthermore, it doesn't state intent. So I've shown you those templates, and I've said this is an element type. What's an element type? In C++, is the definition of that. It's precise in the international standard. For starters, it's something that can be copied. You copy things in, you copy things out. You take addresses of them when you want to pass iterators to them. Inside the iterator is a pointer which has an address. These things can be formalized and specified. They weren't. So if you pass something that can't be copied or something you can't take the address of to a vector, things break in nasty ways because you haven't stated the intent. I said there has to be a type T, which is the element type. I did not say there's an element type, as it obviously should be. The first 3 pages of my Design and Evolution of C++ chapter on templates is an apology for not solving this problem. It's not a new problem. It's not a difficult problem to solve in isolation, but solving it in the context of the other constraints turned out to be quite hard. So basically, I want to be able to say that I have a type named T, and I require it to be sortable because I'm going to use it for a sort function for a container. Sortable has a definition. Again, you can go to the standard and see what it is. It has to be a sequence. It has to have random access, and it has to be elements that you can compare with less than, or a criteria you give it. So very simple idea, but massive impact. So here is something you can write in something called a technical specification, which for some definition is part of C++ 14. For others, it's just a technical specification. You can go and download and use a compiler that's a branch of GCC for it. It'll be part of GCC and Clang next year. Basically, you need error handling that is simple, that solves the problem that is the surface of this for most programmers, which is those awful error messages. So basically, I'm saying that I want a sortable C. So I want a type that meets the sortable criteria C, and then I want to sort it. And let's take 2 containers. I take a list, I take a vector, and I try to sort them. I sort the vector. Is a vector sortable? The compiler checks. Is it a sequence? Yep. Does it have random access? Yep. Can you compare the elements? Let's see, the elements were integers. Yes, we can do that. Fine. Next thing, sort the list. Is the list a sequence? Yes, it is. Is it random access? Nope. That's the end. And so instead of getting these ghastly error messages, the compiler actually says list of int does not meet the constraint sortable. And if you've set your error message level, it will tell you also, and it's not sortable because it doesn't have a subscript operator. That's about as precise and good as you want. And so that's it. Given that, we can do things like overloading. And overloading is one of the backbones of generic programming. It's also known as ad hoc polymorphism. And if you mix it together with generic programming, you get something very powerful. And now that'll work, and you can do the overloading on concepts. So let me see, do I have an example? Yes, I have an example. Let me show you the example here. What if I really wanted to sort that list? I know the standard says you can't, but I can write my own. So the standard says that the sort has to be sortable, and we know what that is. I want to sort just a plain old sequence. A singly linked list will meet that criteria. And so what do I do that? I just say that requires that it's a sequence and its element types are comparable. And then I copy the thing into a vector, sort, and copy it back out again. That's usually the optimal algorithm for that kind of stuff. And now when I sort the vector, I get the vector. When I sort the list, I get the weaker version of the function, the thing that doesn't require sortable, and so I can solve the problem. Let's see. Basically, the overloading is the backbone of things like compile time dispatched on types. So instead of going through a jump table, you let the compiler resolve it. You saw how it could do it right there. And actually, overloading can be quite complicated, but overloading on concepts is very simple. You take the functions. If they don't meet the criteria, they are not there. We don't consider them. If it meets 2 sets of criteria, you simply look at it and see if one is a subset of the other, and if so, you pick the one that meets the most criteria. That's a subset property. And if you have 2 and they're not a subset, it's an ambiguity. And so we have a system that's very powerful and really quite simple. That overload rule is a standard Venn diagram. Just show where the subset of the things are. There's no refinement operation, no concept inheritance. We're simply calculating it from atomic sets of predicates. There's no explicit relationship between a type and a concept. A concept is a predicate. You simply ask the type at compile time if it meets the criteria. Are you a container? There's a set of criteria, just check them off at the compiler, done. Are you an iterator? Done. Are you a forward iterator? Check the things. If you are a random access iterator, check if you've got the properties. It's all computed there. But on these, you break the predicates down into atomic predicates and just run over it. And that means that the overload resolution is simple. Now, this is not the first system that could do things like that, by any stretch of the imagination, not even in C++. It is, however, the first system we have worked on that meets the other criteria necessary. I mean, I have seen a highly rated system for checking of C++, several papers in the most prominent conferences, including some written by me, that had the slight little problem that it slowed down compile times with a factor of 20. And C++ isn't the fastest language to compile. We will get it much faster next year, but that's a different talk. Much faster as in 5 to 10 times faster. But anyway, this stuff compiles faster than the alternatives in current C++. So if you fake the overload or if you use template metaprogram and such, you compile slower than this stuff. And that is on an unoptimized compiler, not an industrial strength tuned compiler. So zero runtime overhead, of course, we must have that. Essentially zero compile time overhead. And we have not imposed new limits on generality. We can actually specify, say, the standard library and slip it in under the existing code. We're not going to do that. We're going to take the opportunity to fix a couple of bugs, but the generality is up there with what we have been using for the last 15 years. Smooth integration with existing templates. A type name is simply the weakest constraint. It says it must be a type as opposed to an integer value. And then you could start adding things like being able to copy it, being able to compare it, things like that. And it has a smooth integration with non-generic programming styles. That's important. So we could say, but what I've been saying here, is it object-oriented? It's got no inheritance, so by some definition it doesn't. It's got lots of static polymorphism, and that was one of the polymorphism in the Cardelli-Wegner paper, for instance, together with ad hoc polymorphism. There's lots and lots of user-defined types, so there's a lot of abstraction here going on, a lot of encapsulation. So who cares? It actually addresses some of the statements that Christian Nygaard made when he described object-oriented programming, not in terms of language features, but in terms of what he wanted to do. So I would claim that I couldn't care less whether it's object-oriented. It is meeting the criteria. It is helping in the way that object-oriented was supposed to help, and it actually fits within the framework of object-oriented programming. And so you look at the buzzwords, and it meets a lot of those, and it meets some further constraints too. So here's a slide that I've been looking at a lot and talking about. Basically, I don't like people having to learn two different kinds of programming, and that was what was happening with C++ over the last 10 years. There was the people who wrote templates and template metaprogramming and generic programming, and they had to think in one way and use a different syntax for it, and then there was all the others who wrote and thought in different ways. And now you have to teach people two ways of thinking, you have to teach them two ways of doing everything. That's very unpleasant. So let's have a look at some code. Here's traditional code, square root. As you learned in the first week of learning how to program, you take a double, and if you give it a double, it'll produce another double that presumably is the square root of the first one. So let's take an integer and try and take the square root of that integer. Can I make a double out of an integer? Yep, this is C++ or modern C, not KNRC. So we can do that and we get the double out, no problem. We take something that is not a double, and like a pointer to a double, and well, you get an error message right there. Compiler knows it. Good stuff. We know that. We learned it in the first week or so. Let's try that with something generic. Let's sort something that's supposed to be sortable. We take something that can be sorted, like a vector of strings, sortable. Is it a sequence? Does it have random access? And can you compare the elements? Yes, yes, and yes, we're home dry. Then we take something that isn't sortable, like a pointer to a container, and it isn't, and you get the kind of error message I showed you on the previous thing. So this doesn't just solve a technical problem, and it doesn't just solve the technical problem in the way that can be implemented in industrial environment and such. It also reduces the sort of overhead of writing the code, because you don't have to have two ways of thinking about it. So what's a concept? It's usually the fundamental concepts of some field. Don't expect to find a new one every year. I mean, of course you can use this as any old programming language construct and express anything, however silly or inappropriate. But the good ones really characterize the domain. Basically, you go into a domain, you analyze what are the fundamental concepts, and they become the predicates we call concepts. So if you go into the manipulation of sequences of data, you get the STL concepts, which are there. And so you get sequence, you get iterator, forward iterator, random iterator, container, regular type, and order type, and things like that. And we have always had concepts. Look into Dennis Ritchie's definition of C, and you will see it says, and this requires an integer type. This requires an integral type. And you look up what that means. There's a set of criteria for being an arithmetic type, for instance, and being an integer type. We've had them. We talk about them. This is why these things are called concepts. In the STL, we have the iterator things. We informally have container, which is not defined precisely in the standard. And algebra has the groups and strings and monads and things like that we've been playing a lot with. So what makes a good concept? Actually, the key thing about a concept is semantics. We can't express that directly in the language. I had to give up on that. I got it into a previous version. It was kicked out because people couldn't see the use for it. What's the use for semantics? The optimizer can't use it. Well, first of all, they're wrong. And secondly, they're wrong about the optimizer too. But I couldn't get it through. But it fits into the framework. We have experiments with it. But you're not going to get it next year. But designing a good concept means designing a semantics and a way of expressing the semantics. Okay, so of course you can define your concept yourself, or you can use a library. The ideal is always to go and use a library first, and we have draft libraries for the standard stuff. But here's the way to define sortable. Sortable takes a type, and it's a sequence of T, and random access of T, and comparable of the value type of T. Value type is the usual phrase for element types, and the reason it's called value types is there are other things than containers that holds a sequence of values, or some values. Or you can build it from primitives. You can say that the type requires something, like you can say A of I and return a reference to a value type. You can compare two of them and get a Boolean, something convertible to Boolean. You must have a begin. Containers have a begin and the end of their sequence, so we can apply our algorithms, and so on and so on. And of course, you can have multi-argument concepts and concepts that takes things that aren't types. Otherwise, you couldn't model C++. And so there's a horrible example there for mergeable. Mergeable takes 3 iterators two that are forward iterators for reading its input, one that takes its output, and then there's some relationships between those concepts. Like you have to be able to compare elements from the two input types and things like that. And you have to write things from the input type to the output type. Now, that's horrible there, but it takes about 2 pages to write in English. And anyway, compilers do not read manuals. So expressing this in code, which is sort of pseudo-mathematics, is important because it's shorter and compilers understand it. And we can get this to work for lambdas also. I mentioned that a lambda translates into a function object or into a function if that's convenient. So basically there is a piece of gratuitous showoff. You can have a function that specifies it wants a number. So that will take any type, and any object of a type that's a number, in other words, any number, and add 1 to it and return the result. Fine. So we can increment 4, and we'll get 5 out. We can do that with a lambda. So the first lambda there, the one that gets named plus, when you give it a number, returns a lambda that will add another number to that lambda. And notice that I am specifying the type of that lambda right there. This is one of the deeper reasons we're not going with the type name T requires blah blah things. Lambdas are there for a shorthand notation, and so we need to get the type built in there. And so I can say plus 4, which gives us back something that'll add 4. Then I can now say increment 4 with 2, and I get 6. Or I could simply just say plus 4 and 6. People who are into functional programming know that this can be done in many, many languages, in many, many ways, and usually with a terser syntax. But this fits into a framework with inheritance, with constraints on performance and ability to manipulate hardware and all of this good stuff. People have claimed this is simple. To my mind, it proves that different people have different notions of what's simple. Let's see, and the whole thing works not just for function template calls. Oh yeah, this is just waste of time. So let's see. I'm supposed to rush and get you out of here on time for the coffee break, and we should have a Q&A also, so we'll skip that. It'll be in the slides that's published. So inheritance is useful, but apparently not essential. We can do a lot of things without it, a lot of real things without it. We cannot do without resource management, because then you get all kinds of leaks, and a garbage collector is not sufficient, because then you end up with the dispose idioms and things like that. We need well-specified interfaces. We have known this forever. We have just had long discussions about what it means. Here's sort of what modern C++ comes up with. And basically, generic programming is a powerful complement to classical object-oriented programming. It could be argued to be a subset of classical object-oriented programming, but it isn't, because people weren't writing code like that, so that wouldn't be classical. But it fits Christian Nygaard's definition of what object-oriented programming was supposed to be. And so I have one example here, which is the old example borrowed from Simula Begin and other early object-oriented text of drawing all shapes in a container. It used to be plotting all elements of a list on a piece of paper. But basically, I want to draw all elements of a container. I want the element to contain pointers to shape. I've been explicit about this, and I'm using the generic algorithm for each, and I am using a lambda to draw these elements. If you took away the requires clause, you would have an unconstrained a semi-constrained container, and the type checking would be delayed till you actually instantiated the lambda. But this one is complete here. And so my question here, is this object-oriented? Sure it is. It's this draw all shapes example. Is it generic? Obviously, it's parameterized on types and uses a generic algorithm. Is this perfectly old vanilla code? Sure, it's got a couple of freestanding functions. And is it sort of data abstraction? Yes, it is. I mean, what do you think the lambda generates? It's an object. So that's it. There's some C++ information in case some of you still thought we were back in the 80s and need a refresher. There's a website, isocpp.org, that has a lot of information, including standards and information. I have a couple of books. Note the Tour of C++. That is all of C++, including all of the standard library, in 180 pages. Of course, it's not in total detail, but if you want a refresher, that's a good place to start. And then there's the C++ Standards Committee's website, where you can get basically everything more than you could possibly want to know about C++. And then I actually managed to get to the Q&A in a reasonable time. So, questions, please.
Hi, good morning and a very good talk. Two related questions, I guess. One is, you talked about concepts, and I kept hearing contracts. Eiffel contracts. I mean, how different are these? I mean, they seemed very similar. And I was wondering what's special here that's, I mean, all the requires and everything. I mean, it's you are specifying some preconditions in terms of I require this, I require this, I require this. It's specifying a contract.
I'm not quite sure I understand the question. I mean,
Eiffel contracts?
Context?
Contracts, Eiffel, the language.
Oh, yes. Let's see. I sort of guessed somebody would ask this question. No, it's not. It's related. It's trying to solve the same problem as constraint genericity in Eiffel, Java, C#, or Haskell type classes. And there's a set of properties here that I think is unique to concepts. It's a set of predicates. It does not have any runtime implications. There's no jump tables. Nobody has to go and specify signatures for it. It can handle values of operations as well as types. It can handle groups of types because a lot of the constraints you want to express involves more than one type. Notice the mergeable example, or even the find if. You can't express the requirements that the function puts on its arguments by talking about one type at a time. So it's not just types. It handles mixed mode operations beautifully. It handles implicit conversions, and there's no requirements of you specifying relationship between concepts. They're computed. There's no requirement of you expressing relationship between concepts and types. They're computed.
Hi. Actually, can you get 2 slides before to the draw all? The next one. No, to the other side.
What?
To the draw all function, where you.
Where is
yeah,
there? That
this
one.
This one. So now we have earlier we specified the types for all the parameters of the function, and now we can specify concepts instead of that. So does it imply actually that this transforms into something like type name, template, type name, container C, C ampersand C here?
Sure. The compiler says something along the lines that there must be a type, let's call it container, and it must be a container. There's a set of predicates. And then it says there's an extra constraint that the container actually must have the value type shape pointer. That is a set of predicates. It breaks that down to a set of atomic predicates so it can compare it with other things. Then it generates a template. If it's used, then it generates the templates for the appropriate set of types.
And one more question. Are these predicates namespaced actually, or can they be namespaced?
You can put them in namespaces,
okay, thank you.
They are perfectly ordinary things. And notice there's a slight overloading there. If a concept is used like that, it acts like the name of the type that it's standing for in the context. Again, a lot of work on simplifying the notation and making it look very much like what we were used to 30 or 40 years ago.
Thank you for the talk. In introducing the Nygaard Prize, Eric pointed out that it took about 20 years for object-oriented programming to go from simula to industrial practice. And of course, there are other examples that take longer. Garbage collection took maybe 35 years. Type classes were in Haskell 25 years ago and are now showing up as classes, as concepts. And
we can argue about that.
And
I keep wanting to write a paper together with Gratuitous Reyes saying concepts are not type classes. It would be an interesting paper. Sorry.
And then another example that took even longer is lambda expressions have been around since the beginning of computation. So could you comment on this long delay from things going from first appearance into industrial practice?
Yes. I was talking to my advisor, David Wheeler, when I was about to leave Cambridge. And one thing he told me was that, well, I asked, is distributed computing a good field to be in? Because that was what I was in, that was what I was interested in. I got distracted a few years later. But anyway, I'm an old sort of high-level hardware architecture systems guy. But I asked, is this a good field to be in? And David sort of scratched his head briefly and says, yeah. There will be at least work for another 15, 20 years because it takes 15 years or so for something to go from the lab into real use. And since I don't know about it, there will be enough for you to do for the next 15, 20 years. So this is an old story, and that goes. And basically, I know this is a computer science area, and I've heard people say this is computer science, not engineering. But there's a lot of stuff that's sort of engineering-like. Notice my list with the tools in it about what things that also had to be met by the by concepts before they were acceptable. It was a slide. The real one is more like 10 or 15 slides. All of these little details. People come up with something that's beautiful and the compiler is too slow or too big. People come up with something beautiful and the teaching system doesn't work. Yes, lambda expressions have been around since the dawn of time, and the education system has been owned by people who like functional programming for about 30 years. Till about 5 years ago, the effect on industry was zero. It takes some time for these things to work in. It's engineering, it's education, lots of things. And object-oriented programming had the similar things. I was walking around in the late 80s and wondering, why are people thinking this stuff is new? It's from 67. I used it when I was in short trousers, roughly. Well, actually, when I was an undergrad. But it takes forever. And I think it's not one thing. There's no simple answer to your question. It's lots of things. It's why did it take so many years for a car to be able to do 80 miles an hour without you bothering. A lot of things, you had to build road, gas stations, suspensions, you had to refine the gasoline properly, you had to make more comfortable seats, da-da-da-da. It's not one thing.
Very good. Bjarne, a warm congratulations.
Oh, thank you,
Bjarne
thank you.
again.